Okay, for class 21, we're finally going to start talking about collision detection. For this part 1, we'll talk about the separating axis theorem. But first, let's talk about circles and spheres, the simplest, the easiest shapes to use in collision detection are circles in 2D or extending those to spheres in 3D. And the reason that's so easy is all we have to do is check the distance between their centers. We just check the distance between the centers, and if that is less than the combined radii of the two circles / spheres, then they touch. And the other beautiful thing about circles and spheres is it doesn't matter what angle they're at. You can rotate these things to any old angle and they're still a circle, right? And so it doesn't matter if the circle's one on top of the other, or one to the left, or it's at some diagonal. It's all very, very trivial. So if you can get away with circles, by all means, drop the circles. For more complicated shapes, we're going to fall back on something called the separating axis theorem. Now, separating axis theorem, that sounds all official and scientific, but it's really pretty simple. Let me just read this. If two convex polygons do not intersect, there exists an axis upon which their projections do not intersect. Okay. Let's say that in English. In English, we're saying if we take two shapes and we project them down onto an axis. For example, I'm saying this green line is an axis. Imagine we put a light up here and we shine a shadow. We make a shadow of the pink object on the green line here, and we make a shadow of the blue object on the green line here. If those shadows don't overlap, that means the objects don't overlap, right? And by extension, that means if there's no way we can come up with any axis where they don't overlap, that means those two shapes must overlap. Okay. Now note, this only works for what we saw convex polygons. It does not work for concave shapes. Like this like kidney-shaped blue thing here, this blue bean, it has a concave piece to it. And that allows the pink shape, the pink is convex, it can kind of tuck in there, and that makes it so there's no way we can separate those with an axis. So the separating axis theorem only works for convex shapes. You're always hearing the old story of the Egyptian pyramids are so precisely built that you can't even get a credit card in between the stones. Well, I got a clue for you. This is why you can't get a credit card between there. They're not all that precisely built. It's just they're not perfect, right? Okay, so that's what we're talking about. If you can take a credit card or something equally flat and straight and slide it completely between those two shapes, then we know they don't intersect. And so that's what we'll be looking for. We'll be looking for what angle do we have to hold the credit card to get it in there. Okay, special case. Now, this is something we've already done, which is the AABBs, the axis aligned bounding boxes. That's what we did in 380. And we're actually using the separating axis theorem there, and it's just a special case where we can take a shortcut. Let's take a look here. Normally, when you have an axis-aligned bounding box, or I'm just going to say AABB from now on, you can just specify that with its opposite corners, the minimum and maximum corner. In this case, I have 1, 2, and 3, 4, right? If we project both of these shapes, the green one and the purple one, over onto the y-axis, we'll check to see if they overlap there. This is something I like to take note of. I like to say that min.y equals min.y. Notice that? The minimum y component we often call min.y. And the minimum vector dotted with the y vector happens to be that same value. Always works. So min.y, in this case, written out long form, min.y is 2. And max.y was 4. In other words, we just look at the y value. And we'll put that on the axis like so. How about the purple one? So for the purple one, min.y is 1 and max.y is 3. Let's put that on the axis. Now we can see that the green line and the purple line do overlap, so this is not going to be a separating axis. However, if we check the x-axis, we find that will be a separating axis. So there's our x-axis, and we found that we can slide our credit card right down there between the 3 and the 4. So therefore, the x-axis, this solid blue line here, is a separating axis of these two shapes. So it turns out that for the special case of the AABB, either the x-axis or the y-axis would have to be the separating axis for those two shapes. And if neither of those axes works, then the two shapes overlap. And so that means we don't even have to do the dot product. We can just check the min.y and the min.x without literally doing the dot, because it's kind of already pre-done for us. And that's just what we had in 380. So that's the AABB case, and we've just sort of phrased it in terms of the separating axis theorem. Now let's see how we can extend that into other shapes.